Alright, because I think I did a kind of poor job explaining torque in class, or at least equilibrium and torque in class, I'm going to go through this a little more carefully, and especially concentrate on the part about gravity applying at the middle of an object. This is a question from one of your homeworks that you did recently. A 30-kilogram diving board that is 10 meters long extends 7 meters over the edge of a swimming pool. With no one on the diving board, what is the torque exerted by gravity? So the part of the board that's over the pool, as I interpret this diagram, is the 7-meter part. So this is the part that could rotate. I imagine the rest of this as being attached directly kind of to the concrete back here on the pool. That's how I'm imagining this, and so that's how I'm going to solve this problem. Well, first of all, I have to know how much of the mass is extended over the swimming pool. Clearly not all of it, but a fraction of it. 7/10 of the diving board is extended over the pool, so the mass over the pool, I'll call that MP, will be 7/10, 30 kilograms. And I just did that using, okay, the whole board is 10 meters long, 7 meters of that is extended over the board, and said, well, that's the fraction then of the board over the water, so that's the fraction of the mass over the water. When I multiply that out, I get 21 kilograms, and therefore the weight of that part of the diving board is 210 newtons. Now I need to know, if I'm calculating torque, I just found the force, I need to know the radius. Remember I talked about that if you have an arm extended out so that gravity is acting on it, and you want to figure out the torque on that arm, you basically pretend that gravity is pulling at the middle of that arm. Now later in the year we're going to talk about center of mass, and I think that will make more sense then. Gravity actually does behave as if it only pulls on the center of objects. And we'll talk more later in the year about why that is. Alright, let's imagine for a minute that on this arm there are two people. Try to give you an intuitive understanding of how this works and why gravity is acting on the center, of equal mass standing on opposite ends of the arm. And we figure out the weight of this entire thing and the torque on this entire thing. So clearly if they're of equal mass, this thing is not going to rotate. Now let's say that we hide these people behind a curtain. And so we're going to pretend you can't see them. I'm actually not filling it in so we can talk about them. But pretend we can't see them. We have each person take one step forward. Neither the weight nor the torque will change. This person will push down just as much over here as they did before, and so will this person. Nothing will change. And we have them take another step forward, and another, and another, and another. Now, to the person making measurements of, say, the torque and the weight, they don't know the people are walking forward. All they know is nothing's changing. And that applies even when the two people are standing together at the middle of the board. What I'm trying to show you here is that we can pretend like all of the mass of an object is located at the center, and we will get the same results for gravity even if that's not true. And on the diving board, all of the mass is not located at the center. But we can pretend it is. We can pretend, hey, there's a curtain here, we don't know what's going on behind it, but we know if they were both standing at the center, this is what we'd get. We'd get the same thing. So we're going to pretend that all the mass is located at the center. Later in the year, we're going to talk about center of mass, and maybe that will clear up this. There is one problem on the exam where you do have to make the assumption, or you do have to calculate the problem as if all the mass is located at the center when finding torque, so just be ready for that. For now, I'm going to ask you to accept it. I'll keep trying to think up a better way to explain it, but once we do center of mass later in the year, I think it'll just really make sense. Alright, so if the mass is located at the center of the extended part, the center of the extended part is 3.5 meters from the edge of the pool. That's half of 7. So now I've got my torque is 210 newtons times 3.5 meters, and I get my torque is 735 newton meters. Alright, remember, pretending that the mass is located at the center of the extended part is how you solve problems with kind of extended arms. Much like this problem that we saw in class, shop sign weighing 245 newtons is supported by a uniform 155 newton beam. Find the tension in the guy wire. This thing is the guy wire. Why don't you pause the video and try this problem, come back and I'll have the answer to talk through real fast. Pause this video, try this problem. Pause the video, try the problem. Pause, try, pause, try. Okay, so here's what I did. First I set up the conditions for rotational equilibrium. Clockwise torque equals counterclockwise torque. And I said the torque from the sign plus the torque from the beam equals the torque from the guy wire. So the sign and the beam, their weights will make this system want to rotate clockwise, and the guy wire is pulling it back counterclockwise. I moved down here for room. So I just rewrote it. T sign plus T beam equals T guy, where those T's are torques. Then I said the tension from the wire holding the sign, which would be the same as its weight because that's all that's causing tension, times the radius the sign is at, 1.7 meters, plus the weight of the beam plus half its radius. Remember we said we're pretending like all of its mass is located at the center, so half the beam equals the tension in the guy wire times the radius of the guy wire times sine 35 degrees. Plugged in my numbers, the tension from the sign is the same as the sign's weight, 245 newtons, times 1.7 meters, how far the sign is away from the point of rotation. The weight of the beam, 155 newtons, and we're pretending all of that mass, and therefore all that weight, is at the center of the beam, so half of its radius, which would be 0.85 meters, equals the tension in the guy wire times 1.35 meters, where the distance to where it's connected, times sine 35, the angle it makes with the beam. Then I divided by 1.35 sine 35, and I got 699.25 newtons is the tension in the guy wire. If you had trouble with that, ask a friend, ask me, make sure you know how to do it. One like it on the test.